start recording, and we will talk. We'll do a little bit of a review of Haskell. So please join the Mentimeter. And there are quite a lot of questions for you to practice some of the Haskell syntax. And we will talk a little bit about the similarities of syntax and syntactic sugar between languages. And we will sort of wrap up Haskell, and we will start Rust. So we have two languages, and you have a third one with Golang. And my advice is that learning concepts is one thing, but then like actually typing stuff is another thing, and you get a little bit more by typing things and getting kind of a muscle memory. So if you type func enough times, and if you type fn and like some Haskell syntax enough times, you will kind of remember it better. So when you just reading it and like watching it and learning concepts is kind of enough. But then if you have to do something, you sort of don't remember the syntax. And to learn the syntax, there is no other way. You have to type it, right? So I do encourage you to basically kind of don't use code completion, just like type stuff, like simple functions that you don't have to be coding like very complex things. You just kind of remember the syntax of how do I define structs, how do I define functions, how do I do loops, things like that, how I do define types. If you do it a couple of times, you will sort of remember it. Like you will have this muscle memory for this. So yes, learning 3 languages in one semester is definitely confusing and challenging, but if you sort of practice on some small exercises, you will get enough enough value out of this. The most important part is concepts. It's not the actual coding syntax, it's the concepts. But as I say, like learning concepts will be a little bit not enough for the exam. In the exam, you will have to type a little bit of stuff. So practice that. All right. So Mentimeter. Where do I have the? Let me. Yep. All right. So please join, and it will be kind of a good practice for some of the syntax. You will have to type some answers. So it's like a good use of time that you actually practice some of the Haskell syntax for the during the class. You don't have to sometimes you don't have to type the answer. You can just like we can have a discussion. So we write code mostly to communicate. We used to write code to communicate with humans, which we still do. And now we also write code to communicate with the machine. So the machine understands the code. And then we kind of prefer clear code. So we prefer code that is like easy to understand, and it's easy to refactor and easy to maintain. So we kind of have this concept of code smell, and code smell means, yeah, the code feels a little bit like off, like it could be nicer or done in a better way. So you should kind of watch it. And there we have this concept of don't repeat yourself. So if you have copy and paste blocks in your code, if you like repeating something, then yeah, you're probably doing something wrong. Yeah, we should not repeat ourselves. So those aspects are really important. You can solve a task in multiple ways, but what we try to do is we try to solve the task in a way that is readable, maintainable, and extendable. So it's like in a nice way. That's why we sort of practice the craft, and that's why we learn, and that's why we learn multiple languages, and that's why we sort of try things out. So this comes with practice, like you've done something and then you have to extend it and you say, oh yeah, if I could have done it slightly differently, and then it would have been easier to extend or easier to test. So try to kind of think a little bit into the future, what the code will be, like what will be the life cycle of the code later. All right. We also have to pay special attention for requirements and the specification, what exactly is being done. So there is this kind of a hype nowadays saying, oh yeah, you say, give me a game, blah, blah, blah. And then the specification requirements are very vague. So the LLM is kind of filling in all the gaps that you didn't specify. And for some people, that's fine. And for some projects, like for some toy projects, that's okay. But when you are writing software which needs to go in production, you have to have a control of what you're actually shipping, what is there. So specification requirements are kind of important. And before we start writing code, this is the most important kind of part of the job, right? So if we are giving a task, we have to clarify exactly what the person who needs the product wants, like what is exactly the specification and what are exactly the requirements. What are the border conditions? What are the limits? What is actually happening, right? How things have to be done. And those are often functional requirements or non-functional. Non-functional, like how fast it should be, how much memory do we have, on what devices it will run, things like that. So those are kind of a non-functional. And then the functional is the business logic, like what it is actually doing. So far we are good, right? You kind of follow the pep talk. So calculate the sum of numbers given by a user as a string, okay? So the user gives us a string of numbers and we have to calculate the sum. Can you solve this? Can you implement it right away? So one more time. Calculate the sum of numbers given by a user as a string of numbers. Okay. Good. So the correct answer is that we cannot start implementing it straight away yet because we don't know everything yet. So what we don't know yet. So the product owner told us, yeah, write a function which calculates the sum of numbers given by a user as a string. What we don't know. What we don't know yet. What do we need to ask product owner? Yeah, that's a non-functional requirement. But let's say the non-functional requirements are kind of up to you. Yeah, exactly. So one of the functional requirements we need to ask is, how do the string look like? How the numbers are separated? Is it like a comma separated list of numbers or space separated list of numbers? Like how the input looks like? Okay. Yeah, what type of numbers? Are we talking about integers or are we talking about floats? So I'm the product owner and I'm saying, yeah, the numbers are integers and are separated by space. So now you have enough information? Or do you need to ask something more? Yeah, what is the value used for? That's a good question. What else? What else do we have to ask? Good. How the numbers are represented? Are the numbers entered in binary or the numbers entered in decimal? Precision. If we're talking about integers, then like it is sort of given that it will be integer precision, but we have to ask at least one more question. Exactly. So how should we handle errors, and what should we do if we overflow? Like what if we exceed the total number of like what is the maximum sum that we are expecting, right? Should it be arbitrary large, or is int 32 fine, or is it like int 64? So what, like how big the number is, right? So yeah, we need to ask all those questions. So it kind of appears very trivial here. Like, okay, of course you can write functions like this, but like there's at least like 6 extra questions you have to ask, right? If you don't ask those questions, you will make assumptions because you have to have answers to those questions. And if you don't ask the product owner those questions, you will make assumptions, and your assumptions will be wrong. It will turn out that the product owner didn't have the same assumptions as you, and you cannot make assumptions. So about the business logic, you cannot make assumptions. So you have to ask those questions, right? All right, so I'm saying the numbers are decimal, integers, separated by space, the most common case. If we have an overflow, we will overflow. So we will loop around. So the most typical case, and the number needs to be returned as decimal integer. So then can we implement this? Yep, I think we can start implementing it. So we basically have to do this. So we have to take a string, which is integers separated by space, and we have to convert them to a list of integers, because later we can sum them up, right? So we sort of are giving a list, we converting it, a list of numbers as a string, we converting it to like internal list of numbers, and then we can run sum on top of that to get the final sum, right? So we decompose our problem into 2 steps, and now we have sort of a partial solution, which is the string to list function, and then we'll have to use sum to get the final answer, right? So sum adds numbers in a list. So we now have to write this function, like add numbers, which takes a string and produces the int. And we have those 2 building blocks, right? So how can we write okay, oh man, 41 questions? We'll be here till tomorrow then. Yeah. So maybe we have to like postpone the Rust until next week. All right, so we have to use sum and string to list and write the add numbers function. So how can we do it in Haskell? What's the solution to our task? So you have already implemented string to list. You have it implemented, and you have a built-in function called sum. So now you're implementing add numbers function. What is add numbers? Okay. So yeah, let me see if I can mark correct. I can't. Why I cannot mark correct? All right, so I will just discuss it. So this one is correct. It just doesn't use the point-free notation, right? We don't need this argument. We can kind of get away without it and use the dot notation for composing our new function out of those 2 functions. The other ones, this one is a good start. The other ones are kind of, yeah, this one is okay, but you need to define what the new function name is. So this one is kind of okay. But you get kind of a feel, right? I will kind of clear the results, so maybe I will be able to mark the I don't know, Mentimeter is a bit broken. Okay, you get the idea. So we have two building blocks. We can combine it together and then have a new function. And our add numbers kind of does sum of the string to list. And the dot notation kind of gets away without passing the argument. So we don't need this argument because this function is like this function, and this function takes an argument, and this function takes an argument. So we just define the function. So in Haskell, it is kind of preferred to talk about functions instead of talking about how data flows, because it's implicit here, right? So it's a little bit simpler. For more complex cases, like point notation is a little bit cumbersome, so we don't do it all the time, but for some problems like this particular one, it would be ideal. That's a super nice syntax and super easy to read, and you kind of get no extra noise in your code. So this kind of a point tree notation in Haskell really rocks because you can kind of compose more complex things out of simpler things, and you reduce the noise, like reduce the extra, parameter passing or everything else. It gets a little bit used to, because in imperative programming, we always think about variables. We always think about, okay, where are my variables? What do they hold? And then how they are being used. Here, we kind of mostly think about functions. We think about the flow, how the program flow happens. And the data just happens to be like secondary. Like the primary instinct is to think about functions, right? All right, so then we need to implement the string to list, right? So we assumed before that string to list was implemented. Now we have to implement it, right? We have to actually implement the function string to list. So how could you do that? So that is like pseudocode, like because it's not the Haskell syntax. So we implementing that function, which potentially takes a string argument, right? So we need to take a string and return a list of numbers. This one is a little bit more complex. So the previous one was easy. Like we have to do sum on top of the string to list. That was easy. This one is a little bit more complicated, right? So yes, we could do read string, but that gives us remember the string is kind of the string is 10 space 20, right? So that's our string. So read will not work because that is not a Haskell type. This is something kind of not yet ready, right? So if we need to read, we kind of need to first turn this we have to sort of turn that into a 10 and then 20, right? So if we turn this into this, then we can read individual things, because if I read 10, then I will get actual number 10 as a int, right? But I cannot read this. So we have to do kind of a like extra step before, right? So how do we do it? Excellent. So this is a correct solution. We have to words the string first. So words will convert this into this, and then we have to map read onto this. So we're gonna get an array of 10 and 20, right? So we have to map read to this, but to get this, we have to call words on this. So again, we have data flowing, but the data flows in such a way that we first do words on the data, and then we apply map read to what words returns. And again, we can write it like this. We say do words first on the data, and then compose it with map read and do that afterwards. And we don't need this variable here or here. So instead of using the brackets and the variable, we can replace it with the dot and get rid of the variable, right? When you're learning Haskell, you write like this, it works, and then you say, okay, I will refactor it because now I can see, I can remove this and put a dot here and remove this, and it will be nicer, right? You don't necessarily write it immediately, right? Because it's hard. It's kind of hard to write in this dot-free notation. But once you write it in the dot-free notation, then it's like really easy to read. It's kind of, you see immediately what's going on, right? It's a little bit more compact, and it's simpler to read, right? So this is preferred syntax, but you don't have to write it immediately like that. You can write like this and it's fine, and then you can refactor it to point-free notation afterwards, right? Will this work? Of course it works. It's not wrong, it's fine. But it has this like small smell, right? It could be a little bit more beautiful, right? And you sort of feel, yeah, it's okay, it works, but it has this very tiny code smell that we're doing something which we don't have to. Like we're repeating string. Don't repeat yourself. Get rid of this. It's easier. Like it's kind of, you know, simpler. So if you're repeating yourself, if you're repeating your variable in multiple places, maybe you don't have to do this, right? All right, so how are we doing? I don't know. We lost the... I messed up the Mentimeter completely. I don't know why. Turn off responding. What? Okay, let's see. Okay, maybe on the next one. So that is the sort of the definition of string to list. So we have the final solution, right? We have two our functions, and they are kind of both written in the point-free notation, right? Why? Why do we care? And why we sort of talk about it? So I think it was task 6 or task somewhere along those. I think it was 6. I was checking last night, and I think it was 6. We are doing kind of a decoder for messages, and we were finding the numbers which had certain properties, right? So we had to find the maximum number and the minimum number, and it has to be unique. And then we were finding the middle point, and then we were doing certain things, right? So this is like the solution written in do notation, and we are using this combination. Instead of brackets, we're using the $sign, right? So this is the same as if I put this in the brackets, right? And then it's the same here. This one is the same if I put those in brackets and then those in brackets. So instead of using brackets, this code uses this, right? And it solves this sort of communication puzzle for calculating the numbers, right? So you can read the code and you can see, okay, we are kind of getting the list of numbers because we're doing map read words. and the message is passed from here. And then we're getting a minimum value, we're getting the maximum value, and those are giving us an error because we have either error or everything is fine. And if this gives us an error, the error is minimum. If this one gives us an error, the error is maximum. And then we're finding the midpoint. And then if we're checking if the midpoint is even, then we do this. If it is not even, we have an error saying the communication interference, right? So it's a normal code. It works. It's fine. But it has a little bit of a smell, right? So one smell is with this use of those sprinkled, what's that? Dollar sign, right? So we can kind of refactor it. So this is a solution which was found by one of the students last year. And then you can refactor it. You can make it a little bit nicer. And you can kind of write it like this, right? So instead of using the dollar signs everywhere, we sort of composed it here with, we moved the dollar sign to here, right? Can we get rid of the message? Not really, because we have to do this do notation, and for the do notation, maybe it is kind of easier to have the message in. Maybe we could get rid of it, but like normally we sort of say we have to kind of make the code readable, and then having this dollar sign here is okay. But we sort of said there is a function which is doing something on the data, right? So it's kind of the way you think about it. That both solutions are exactly the same, right? But it's sort of like this one reads, do this first, and then do this, right? And this one says, do this on the data. And this is composed of two things, right? So it's a little bit like they are equivalent, they are the same, but the way you think about it is a little bit different, right? And it's the same with this, right? Same here. We're saying if the middle point is even, do this on the data. Like it's one function. And this function is composed of certain things. We're doing certain filtering, we're checking the length and then wrapping into the monad. But this is like behavior and this is data, right? We separate behaviors and kind of think about behavior separately from the data. We try not to have the data represented like kind of explicitly, right? And in the previous one, we had it like, do this filtering, and then check the length, and then do the return. And we were kind of like forcing a more imperative kind of style by putting those things here instead of composing, right? The dot composes the solution. The dot says, combine those two things together and create one function, right? So it says, compose those three things into one function and then apply this one function to this. As I'm saying, they are equivalent. It's just the way you think about it is different, right? So the way you write your code explains how you thought about the problem and how you solved it. So we have this concept of pyramid of doom. Have you heard of this before? If you programmed in JavaScript, you probably did. It's this sort of if-else code, right? Have you seen it before with callbacks? You probably have seen it before. So this is called the pyramid of doom, where you have those nested if the post like contains the correct passwords, then if this one, and blah, 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 and then you have this sort of unrolling of the checks. So we don't write code like this. This is a nightmare. This is a nightmare to maintain, and it's so error prone that we kind of don't like this. So again, this is a code from last year. So a student wrote the code message, improved, and I changed the name. It's not really improved. And we can see there is like this really nested kind of if statements going on, right? Will that code work? Of course it will work, right? So we're saying, okay, convert the string into the numbers, check the length, If the length is like wrong, then we say like we have an error. If we don't have an error, we're checking this one. If we have an error, we shortcut. If we don't have an error, we do this. If we have an error, we say what error it is, and so on, right? It's a normal code. It looks really like Golang style. You have those if statements, and if there is an error, you're shortcutting, you're kind of returning the error. If there is no error, you continue, right? So nothing magical here, very imperative style. It works, but it feels kind of smelly, right? It feels wrong, like there must be a better way to do it, right? This one is like kind of ugly looking, right? So we shortcut here with the if statements on the positive. You can turn it around. What will happen if you turn it around and you have, if something is correct, then and you're doing the correct thing, but else is the wrong thing. The else is the throwing the error. What will happen? What will happen is that you will have this a little bit more like this, and the errors will happen kind of here, and the positive thing happens here. And you, first of all, you have a little bit difficulty matching, like, what is this error from? Like, why I have this error exactly here? So it is because of something here, but you have it like spaced, right? Having it together is better. So having the errors kind of immediately where something went wrong is always better, right? And the positive thing is sort of like you don't have this the other end of the doom, right? You have this sort of just one side of the doom. All right, so let's have a look into some. So we have to avoid pyramid of doom. We have to structure our code in a better way. When we can, we should restructure our code to use do notation. But we also have to understand syntactic sugar. So the languages that we use often have syntax that helps us to make the code more readable. And it is called syntactic sugar, right? So syntactic. It refers to syntax. And that refers just to the tokens, to the structure of the language. So syntactic sugar. So this is a term which means you have different ways of achieving the same task in a language. And with the syntactic sugar, you have a simpler way to do something because the language kind of offers you this sort of shortcut, right? So the syntactic sugar is like a additional ability for you to express something in a different syntax, but achieve exactly the same thing, right? And in Haskell, this is the do notation, right? So do notation is a syntactic sugar, which allows you to write kind of a code in a very imperative way, which is equivalent. This code is equivalent to you doing like the inner functions. So you can have some sort of a bind operator, and then you're calling kind of you're calling like a inner function with x, and then you're sort of doing something with x, and then you're calling another inner function, and so on, right? So you kind of have this syntax, which has the kind of a functional feel with the inner functions, replaced with do notation, and the inner functions are kind of hidden from you. So they are sort of replaced with this arrow notation, right? So instead, so if I have some function f here and I'm getting x, right? So this is an equivalent of me saying call f bind to something, because here I'm calling g, for example. So then I would have something like this, and I would have x, which is the one which was extracted from the first function, which was sort of getting the value out such that I can pass it to g, right? So I will have sort of a mechanism for extracting the value out of the context using the inner functions. But in here, I'm doing it just with the kind of an arrow notation. So it achieves the same thing. It's just syntactically nicer to write and nicer to read, right? So one example of this is asynchronous programming and callbacks, often leading to Pyramid of Doom. And there is JavaScript kind of Node.js structure where you're calling something and you're passing the callback, and then you're doing certain things, and you have to call this callback from inside. So we're going to see that. And then in Kotlin or Haskell, we use this imperative style of this do notation, where we can extract the value from the context using kind of a nicer syntactic sugar notation and have a kind of a much nicer code. So let's have a look. So you're going to learn Kotlin in the 5th semester. So nothing really to worry today, but this is a JavaScript, and we have this typical situation where we have to fetch data, but this fetching data can fail. It can have like a normal response, or it can have an error. And depending on what happens, we have to pass, either we call the callback with the empty error and data, or we calling this callback with an error and empty data, right? So it's sort of like in Golang as well. So we have this callback which accepts error, comma, data, and then we kind of either do this or do this. But we kind of nesting, like we doing this call, this asynchronous call, and then we have to have this dispatch of whether we routing the callback with the happy path, or if we are routing it with the unhappy path, right? And then so this is on the, this is the unhappy path for fetch. And then we are parsing the JSON, and then we have again happy path for parsing JSON or unhappy path for parsing JSON. So we have this sort of already a little bit of a pyramid of doom, because we have this referring to fetch and this referring to parsing. And it's already kind of difficult to read, right? So the yeah, so this is our callback. So the callback has error data, and then we sort of are handling it like yeah, this is like an error handler for the callback. So we're not doing any business logic here. We're just kind of handling error. This is the kind of the business logic which does the data fetch asynchronously, right? So then if we want to, this is using this sort of inner functions, because we say, okay, we're doing this and we're passing a function as a parameter, and then this function is kind of used here. And then for this one, we're passing also the function. So we're doing those inner functions which are kind of going in and in and in, and then they are used to sort of unroll this dependency, right? So then what we can do is we can do this do notation, same as in Haskell, and this is like this is an example in Kotlin. So instead of having the passing of the callbacks, we say we have this kind of arrow. We say we can do fetch asynchronously, and it will return us later the value from outside of the fetch context, and this response will be correct, or it will be wrong, and we have the unhappy path in the catch, right? So this is a happy path, this is a happy path, and this is a happy path. Unhappy path gets shortcutted to the catch, and the error catcher kind of handles what was wrong, right? So instead of passing the callbacks into the fetch, we're saying the happy path is handled here, and the unhappy path will be kind of shortcutted via this kind of notation to the catch block, right? So then to call this, we just calling it like this, because we don't have to pass any callback, and the error handling kind of happens already in this function in here. In previous case, when we call the fetch data, we have to pass this inner function, which is our error handler, and the error handling happens here, not inside here. And here we are passing the functions inside, right? So which one is nicer to read? Of course, this one is nicer to read. It's more concise. We have less noise. Can we pass a function here and handle error here? So yeah, we could. We could pass an extra parameter, and then instead of doing something here, we could call the handler for this, or even return. Can return error from this function, and then this function could do something, right? So this is like, you can see this looks really like Haskell because it uses this do notation with the value in the context, and the context has happy and unhappy path, and the unhappy path is handled by the exception in the catch block, right? So does it sound similar to Haskell? Yeah. All right, so then Haskell composition, we talked a little bit about this for the dot notation, but here we're coming back to basics. We're really going back to like foundations. So let's have a go. I hope the quiz will work. 3 plus 2. Perfect. So one more comment about the syntactic sugar. Do you like languages where you can do the same thing in multiple ways? Or do you prefer languages where there is only one way of doing something? It depends, right? If there are multiple ways of doing something and they are kind of the same, then it sucks that there are multiple ways. But if there are two ways and one is really complex and really a lot of like symbols and one is really clean, like the do notation, right? So the do notation is a syntactic sugar for the bind operator with the inner functions, right? So this is replaced with the do notation. And then you have ability to do the same thing in different ways, but one is clearly kind of has value, right? The syntactic sugar has value, right? So we kind of say it depends, but most of the time syntactic sugar is added to simplify something that is a little bit more complex without it, right? So it was added on purpose, right? So the most the language which is kind of typically considered as the sweetest language, which has the most syntactic sugar, is Scala. So Scala has always multiple ways of achieving something, and they have a lot of syntactic sugar, right? They kind of like it. So it is called like the sweetest language there is. All right, so let's go to the next one. So we had the 2 plus 3. That was simple. Now we have this. Yep, it is still 5. And now we have this 2 plus 3 and a function taking an argument, right? And we have, we know that the multiple functions always kind of rope up to be carried, such that this actually is a function which takes one argument, which takes the argument which is 3 and gives us 5. And this is a function which takes one argument, which happens to be 3 and gives us 5. And this plus is kind of in the infix notation in the middle, right? We use those single ticks for functions to be kind of placed in the middle. So you can say this is a little bit of a syntactic sugar, because really what happens is this, right? we just use this because it's nicer for us to read. We are kind of familiar with the infix notation for certain operations to be kind of in the middle. But kind of really what happens is kind of this, right? All right. How about this? So this plus here does not really look like a function. In fact, the 2 plus doesn't look like a function. It sort of feels more like there is an operation happening, arithmetic operation. But in Haskell, everything is a function. Everything is a function. And this is a binary function, which takes 2 arguments, which we know from Haskell that it's not possible because all functions in Haskell take only 1 argument. So that means if we have something that looks like it taking 2 arguments, it means this guy takes 1 argument and returns as a function, right? So actually this plus is a single argument function, which returns us another function, which takes 1 argument, and that one returns as a sum, right? So this is kind of equivalent to this. That's why they are kind of, this is a syntactic sugar for this. So here it's still 5 because we just said, we just entered this operator, this function, to pass this argument to this, right? Simple. So perfect answer. So this is a function as well. So what happens if we do this? It works perfectly fine. And in fact, if you look at this 2 plus 3, this is a syntactic sugar for this, right? Because this one takes a left-hand side and a right-hand side and passes the right-hand side to the left-hand side function. And it basically is doing that. Correct? All right. So let's do something a little bit more mind-bending, a little bit more challenging. Flip. What is flip? Flip is a fun function which takes 2 arguments, 3 arguments. Flip takes 3 arguments. So flip takes a function, argument A and argument B, and it calls the function f with those arguments flipped. Right? That's what flip is. So it basically is a mechanism to call a function in such a way that the arguments are flipped. So now we're calling this function with those 2 arguments flipped. And it is a compiler error. Yes. Why? Why it is a compiler error? Perfect. Because 3 is not a function. So f must be a function. And flip takes the function and applies the arguments in the opposite way. In our case, f is this function, and this function needs a function on the left-hand side and a value on the right-hand side. So the first argument is always the left-hand side argument. So we can rewrite this syntactic sugar into this, which means this needs function on the as a first argument. And then this guy here will flip the argument. So it will put 3 as a first argument, and 3 is not a function. Good. I think it's a little bit clearer. And let's see if the leaderboard works. Hallelujah. We're back in the game. So how we are doing? Clippy is doing so far really good. All right, so let's continue. How about this one? Perfect. Not so hard, isn't it? Okay, another one. Ooh, it's a little bit complicated. Will that work? So it will not work. And why it will not work? Why there is a compilation error with this composition? Why we cannot compose flipping with this next function? So yeah, so but like focus just on this. So it is true, like you can sort of analyze the parameters to this function, but let's focus just on that function alone. Why this is not a good function? Why this does not work? Yeah, after I get the correct answer. So why this does not work? Exactly. We have a problem because this thing here composes functions that at the end have to take one argument, right? So, and this function here expects 2 arguments. This function here expects 3. So we have a bit of a mess, right? So this dot, like when you have something that takes a dot, so you have, you know, something else, and then yet another thing, and you have the dot. You know there will be a value being passed to this guy, and then this guy will create one value which will be passed to this guy, and then this will create one value which will be passed to this guy. That's what this dot does. So if you have functions which are binary or tertiary, it gets really complicated because they don't kind of compose well. This guy expects 2 arguments, and then this guy expects just 1 because it has this dot. So you have this kind of a problem of the composition. We cannot compose 2 functions which each takes different number of arguments, right? That does not work. They don't fit. So it's like with this railway-oriented programming, you have one component which has 2 slots and another which has 3, and it's like, okay, like how can we do it? Like you have to have components which kind of match. All right. Would that work if they both were taking 2 arguments? It kind of depends. Sometimes you can do this, but the easiest way of thinking about the dot is to think about one-to-one. All right, let's have a break. Let's have a break. 2 minutes. All right, 10 minutes. Let's be generous. Cool. Yeah, it's a list. So if you are coming from C and you see something like this, you say, yeah, it's a list. But if you're coming from Haskell, you say, oh, it's a semigroup. It's also a functor. It's also an applicative functor and also a monad, right? It's a very powerful thing. The one thing that it is not, it's not a type. Why it is not a type? We will come back to it. But what if I said it's this? Would that be a type? All right, we will come back to that. So let's do maybe. So remember, this guy and this guy, and maybe. Maybe. Yes, it's all of those things, but it's not a type. Maybe is not a type. It may be shocking and it may be really confusing, but we often say maybe type. Use a maybe type. Maybe on its own is not a type. Maybe is a type constructor, but it's not a type yet. Maybe int is a type, but maybe is not a type. I cannot say my variable v is of type maybe. I cannot do this. But I can say my variable v is of type maybe int. This I can do, right? Same here. My variable v is of type array of ints. But I cannot say my variable v is a list, a generic list. I cannot have variable as a generic list. Haskell is a strictly type language. You need to know the type of your list. You need to know the type of your variables, right? So this is a generic type, which is not a type. It's a type class. No, it's not type class neither. It's a generic type. This one is a concrete type. This one is a concrete type. This is a generic type, right? All right. So structures, value in the context. We have it last week, so should be easy. So what is this? Yeah, we have this terminology, like complex terminology. We didn't have to deal with this in C, and we don't have to deal with this in Golang. But in Haskell, we have to deal with it. And in Rust, it's a little bit like that as well. Yes, it's a data constructor. We can construct values from it, but it's also a type constructor, right? So if I if I use this as a function and I pass 1 to it, then I will end up with a list with 1 inside, right? So it's a value constructor, right? But if I use it as a function and I pass int to it, and int is a type, then I'm gonna end up with this, and that's a concrete type. So I can construct a concrete type using a type constructor, right? It's a kind of an interesting concept because in languages up to now, you did not construct types. You had templates, and you can kind of syntactically create kind of types based on the syntax of the template, like in C++. But here we have like part of the language, like you can construct data, but you can also construct types, right, from generic type constructors. Okay, so if you give it a type, you will get a concrete type. So for example, if I give it int, I'm gonna get a list of ints. And so this is like a function, like a real function, right? It's not like some template magic. It's just like a normal function, which given an argument produces like an outcome, right? Okay, so this is also an empty list. Is it, right? An empty list is a value. So what type? What type is empty list? So if I ask the GHCI of what type is this, like give me a type, what it will, and I treat it as a value. So I treat it as an empty list. What type will I get? So I will get a list, and then what will be inside? A small a, which stands for a variable, which means any type, right? Which means it's a generic value of possibly any type. And this one, what is this? It's an answer to the universe, of course, but what else it is? It's a int, or is it a number? In C, it's an int. In Rust, it's an int. But what it is in Haskell? It's a number, right? Num. And what type is num? Is it an int or is it a float? We don't know. It's a generic number, right? So it's a generic class representing a class of numbers, but we don't know what it is. It's polymorphic, right? It can be a float, it can be an int, like we don't know. It depends how it's used later. It's a literal, which means it represents a value. Literals are something that represents what they actually are, right? So numbers like 13, it's a literal. It represents a number. In C, it represents an integer. A string is a literal, which represents what it is. If I have something like this, if I say T, if I do this, what is this? It's a literal of a struct which has a value T with this value, right? So this is a literal of some struct type which has T string, right? We don't know the name of this type, but this represents the value. It's kind of a concrete value, right? So languages which allow you to kind of express more complex data structures or values just by literals are kind of more powerful because you don't have to provide a mechanism to build them, right? So imagine that you have a language where you cannot say I have an array of 2 numbers. Okay, this is a literal which represents a list or array of 2 numbers. And if you don't have a language like this, you have to have a variable, and you have to have v add or push, you know, string 1 and v add string 10. And now v represents the value which this literal represents, right? But for literals, you don't have a variable, like they are what they are directly. So it's here. But this one is generic. And it is polymorphic. So this one is very polymorphic because it represents any possible type. There is no constraints. This one is more constrained because it represents numbers. So what does it mean that something is polymorphic? Have you heard this word before? Yes, you had object-oriented programming. So you definitely had to hear this. The word comes from poly, which means multiple, and morphic, which is like changing shape, morphing, right? So it means you can have something which can be treated as different thing depending on the context. So it's like this number 42. It can be an int, or it can be a float, or it could be fractional number, and like we don't know, like it's poly, it has multiple possible shapes, right? So why it is useful? Sorry? Yeah, because you can reuse it. You don't have to duplicate multiple literals or multiple functions multiple times. You can kind of have just one and then use it in different contexts, and it will be the same thing, right? So if I have a function f, or let's say we have an adder, right? I have an add function which takes two numbers, a and b, and I kind of specify that yeah, so in like, let's do it properly in Haskell. So I have an add function, and the add function is a function which takes a, which is a number. What's the syntax? This arrow is here. This one is like this. So then it's like this. So then I have add, and I say add is the same as plus. I'm using like the 0.3 notation. So I'm kind of cheating completely. If I were to kind of be very explicit, I would have to say add AB equals A plus B. But this is like, do not repeat yourself. So like, okay, let's get rid of those guys. So I end up like this. So then if I say add, and I say 7 and 8, it's going to give me 15. And if I say add 7.5 and 7.5, it's also going to give me 15. And I don't need two versions of this function, one taking ints and one taking floats. I just wrote it as a generic function, and then it's polymorphic because I can apply it to ints and I can apply it to floats. So I just have one function, right? Otherwise, I would have to have 2 or 3 for fractions and so on, right? So it's like to make our code more concise and like don't repeat ourselves. All right, so let's keep moving. Otherwise, we're gonna stay here till the evening. Maybe. It's easy because I gave you the answer like before the break. It's a type constructor. Perfect. You are paying attention. Very nice. Why it is not a data constructor? Because if you use maybe with something, you cannot construct a value. I cannot say maybe 10. Maybe 10. I cannot do this. To have a variable which says, okay, it's maybe 10. No, that does not work, right? So it's not a data constructor because I cannot create value with it, but I can create a new type with it. Right. All right, so next one. What are data constructors for maybe? Maybe has one or two or more. I don't know how many. Data constructors, what they are. Just is good. Nothing is good. Let me see if I can mark correct answers. No, I cannot mark correct answers. Why? Anyway, nothing is good. Nothing and just is good. Just and nothing is good. Yeah, all those just and nothing are data constructors. That's correct answer. Unfortunately, I cannot mark the other answers as correct, which is weird. Okay, I can. I can. This one is correct. This one is correct. This one is correct. Perfect. I had to refresh my Menti. Okay. This one we've done last week, so you should be pretty straightforward. But now you have to type. Muscle memory. All right, let's see. Oh man, it seems I have to refresh it every single time. Yep, I have to refresh it every single time. So that sucks. So the other ones are not correct. Um, this one would be correct, but we don't have this function in the context. You just put it into the context, but the function is not in the context, right? So this would work, but it's not what the question asks. So this is like working, it's correct. It will give just 20, but it was without the just. You have just pure function. You don't have a function in the context yet. All right, so then next one. So we had to use fmap before. Do we still need to use fmap here? This one is correct. This one is correct. This one is correct. Yeah. All right. So yes, of course, we just use fmap or map. Fmap for lists is defined as map anyway, so they are both exactly the same. And we can use the infix fmap notation, which, yeah, this one is kind of correct, but the typo is the multiplication is on the wrong side. I don't see it in the answers. Let me see. Yeah, I marked it as correct. Why it didn't work? Yeah, I marked this one as correct, but it didn't refresh for some reason. Yeah, anyway, let's move on. Functor. So we are applying pure function to something. So that's what functors are. Now we have functions in the context. So a little bit different. This one is correct. Yeah, that's pretty much it. Fmap does not work. So this one does not work anymore. This one is for functors, and this is already in the context. So for this one, we need a pure function. All right. Here we have applicative functor, more power. It allows us to wrap a function inside a structure. We have a wrapped functions. All right, another one. Yeah, we covered that last week, so that's easy, hopefully. This one is correct. This one is correct. Right, so we cannot use fmap because we have functions inside the structure. So fmap will not work. We have to use applicative, apply. So this one is correct, this one is correct. This one, we don't have justs. We just have what we have. So, and this one is correct. I mark them as correct. I don't know why that does not refresh. Stupid Mentimeter. Yeah, they are correct now, right? Oh, come on. Yes. So it does not refresh. It marks them as correct, but does not refresh. All right, next one. Easy. Yep, nothing. That's correct. Nothing happens. This one. Compiler error. We cannot fmap functions in the structure to our values in the structure. It's not gonna work. We have to use applicative apply. So a compiler error. How about this one? Can we map nothing to just 10? No, we cannot. It's a compiler error. Same reason as before. All right, how about this one? Yes, compiler error. Because the function needs to be on the left. So, perfect. You're getting somewhere. All right, a little bit more, one level up. So we have pure function, and then we have a box in the box. We have two boxes. We have the outer box and we have the inner box. Okay, and it's not gonna work, right? Because fmap just peels the first box. And then the second one, like, multiply by 2 is not gonna just work with just. So how can we do this? How can we apply multiply by 2 to the inside value inside the inner box? What do we need to do? It's a very common problem. It's a very common pattern where you are having something in a structure which in itself is inside a structure, and you need a pure function to apply to it. So then what do you need to do? Good thinking, yeah? You kind of need to apply fmap twice, but unfortunately this notation will not work, that syntax will not work, because the fmap, like you would have to compose it, right? The arguments for that fmap kind of don't match the type that this fmap expects. So you do need to do two fmaps, but you cannot use this syntax. Let's solve this one and we'll have a break. So you cannot like this one is like trying to cheat, trying to extract the just 10 first and do something with it, but you cannot, like you already have it like this. This is a parameter. You have to use both. Mm, why just don't use fmap? Like you can say compose fmap. So you're saying fmap and fmap with the dot. So you can kind of say, you know, apply like or with brackets, you can kind of say apply this to this, but this is fmap to this, right? So you have to do fmap twice. Let's finish this fmap twice business and then we'll have a break. So how about you have three? You have to use fmap 3 times, right? So let's finish this. How would you multiply just 10, but 10 is inside the list? So how would you do this? It's the same as the previous one with just. It's exactly the same. You have to use fmap twice. So how can you use fmap twice? Okay, let me check which ones are good. So, yep, that one is correct. Um, the one with the dot is probably good idea, but it will probably not like the notation for infix. So if you use fmap, it would probably work. But again, you'd have to say what you're mapping. So the two fmaps have to go like up front first. So this is not correct technically, but you can play with it. So as I said, this is a very common pattern. We often use it. This is from the SDL lab, which we had last 2 years ago. We were doing something with SDL library, which is like for game, for screen, for keyboard, and so on. So it's like a simple media kind of library for manipulation objects on the screen. And then you have this sort of situation where you have to map from integral, and then so you have two boxes. One box is the SDL window size, so you're kind of getting values from one box which is inside, but the values are kind of integral, and then you need to map them to like integers. So you have to get the from integer pure function applied on this sort of fmap that you're getting the values from the inner box, right? So you have kind of an inside box and the outer box, and you're kind of applying the inner function. So this is a pure function which goes into the value which is inside the second box, right? And we have one fmap here and one fmap here. So this one is the mapping into the box, the inner box, and this one says take this, peel the first box and do that one to the inside box, right? All right, so break. Break it is. Another 10 minutes. All right.